So we're going to move on to the last part of chapter 23 and to cover some odds and ends. So first off, if we're talking about intervals and tests, we should know that confidence intervals and hypothesis tests by now are built from the same concepts. In point of fact, they are two perspectives of the same question, which means the confidence interval provides a range of values that a parameter within would cause us to fail to reject the null hypothesis, aka our confidence interval contains all possible null hypothesis. That's what it means by the confidence interval provides a range of values that a parameter within would cause us to fail to reject the null hypothesis. These are all potential nulls that could be true. Values outside of the confidence interval would lead us to reject the null hypothesis. A confidence interval with confidence C contains all the plausible null hypothesis values that we would fail to reject by a two-tail hypothesis test at an alpha level of 1 minus C. Again, if we have a two-tailed test, our alpha level is 1 minus C. So a 95% confidence interval matches a alpha of 0.05 with a two-sided test. Note, when we have a picture and our normal curve, what we're saying is we have two sides, and that is our 95%. Which also means that if we are shading on the outside, on both sides we have 0.025, 0.025. And that's usually where we have our cut line and our inverse normal or inverse t. So confidence intervals are naturally two-sided, so they match exactly with two-sided hypothesis tests. That's when they're pretty easy to do. When hypothesis tests are one-sided, though, the corresponding alpha level is 1 minus c over 2. So if we want a 90% confidence interval on a one-sided test, let's say greater than or less than, then we would do 1 minus 90, or 0.9, all over 2, which means we'd use an alpha of 0.05, not 0.1. But with a two-sided test, with a 90% confidence interval, it would be 0.1. Next, if you are going about conducting research, and we know that smaller margin of error means higher accuracy. And if we want to shrink our margin of error, we also need a larger sample size. So the question goes, before you go about conducting and collecting your data, how do you determine the sample size that's necessary? So to find sample size needed for a particular confidence level with a particular margin of error, we can solve the equation. Now, note that margin of error is our t-test critical value times our standard error, which is our sample deviation, sample standard deviation, divided by the square root of n. And our confidence interval is given by our sample average plus or minus our critical value times our standard error. Now, this is all great, but the problem with this is when you go about collecting your own data, you don't know what the sample standard deviation is because you haven't collected the sample, and you don't know what n is. And that's what we're trying to find here. So the problem with using the equation above is that we don't know most of the values. However, don't fret. We can overcome these. You can either use S from a small pilot study to establish the sample size for a more comprehensive study, or what we're going to show is we can use a two-step process by using Z star first. So we're going to use a critical value given our confidence in place of the necessary t value, and we'll calculate n from there. So we will calculate a sample size and then use that sample size as our degrees of freedom to find our new critical value. So it's a two-step process in finding our sample size for our t-test. So what we're going to do is we initially estimate n by using z. This gives us our first n. Then we use that for our degrees of freedom to solve for our critical value. Suppose an initial convenience sample has a mean of 135 and a standard deviation of 32. How large would you need to estimate the population mean with 95% confidence interval and a margin of error of 5 pounds? So I'm going to go through this as a separate calculation, and then we'll come back and go over the notes. So with the problem that we were given, the sample average was 135 pounds, and the standard deviation was 32 pounds. What we're going to do is we're going to try to find the 95% confidence interval with a margin of error equal to 5 pounds. So we first are going to use z and z star to estimate t star to get our sample size. So find n is the option. So first we're going to use z. Now we know that margin of error equals z star times s over the square root of n. So if I fill these in, and if we need our critical value for a 95% confidence interval, we can just do inverse norm, and it can go either way. We can go 0.025, since this is a 95% confidence interval, 0 and 1, because this is a standard normal model, or we can do 0.975. Either way is fine. This one will give you negative 1.96. We know that's going to be positive because it's plus or minus. Either way, it should be the same. So we can start plugging in our numbers. We have 5 equals 1.96 times 32 over the square root of n. And just to solve for n really quickly, we would divide by 1.96. So we would get square root of n equals 1.96 times 32 over 5, which means n, if we were using z star, would be equal to 1.96 times 32 over 5 squared, which gives us 157.35. So this is the n that we're going to use to then further dial it in using a t interval. So knowing that we need now our critical value for our t, we use inverse t. Now in this case, we're going to use n with a 0.025, same confidence interval, but n, if this is n, our degrees of freedom would be 156. So we're going to say 156, and that's going to give us a critical value of 1.9752. This will give us a critical value of 1.97529. So again, now that we have our margin of error formula is equal to t star of n minus 1 degrees of freedom times s over the square root of n. We're going to fill this in again to get a more accurate representation for what n should be. We will have 1.9752 times 32 over the square root of n. And then if we solve for n one more time, we get n equals 32 times 1.97529 over 5. And that will give us a sample size of 159.817, which is about 160, sample size of 160. So after going through that calculation, to wrap up sample sizes, sample size calculations are never exact and they're rarely understood. The margin of error you find after collecting the data won't match exactly the one you used to find n, and that's okay as long as the margin of error is less than that required to find n. Likewise, the sample size formula depends on quantities you do not have until you collect the data from a sample. You do not have I'll say that one more time. The sample size formula depends on quantities you don't have until you collect the data from a sample you don't have. But using it is an important first step. This gets us started. Before you collect data, it is probably a good idea to know that the sample size is large enough to give you a good chance of being able to use the statistical techniques that you hope to use to answer the question. So this is our first step when we're going out collecting data as researchers. Lastly, degrees of freedom. If we only knew the true population mean, mu, we would find the sample standard deviation as, if you recall this formula, S equals the square root of the sum of all of the variances divided by our sample size. But we use X bar, or the sample average, instead of mu, our population mean, and that introduces a source of variability. When we use xi, this is just some data value, minus x bar squared, rather than the sum of some data value minus our population mean squared to calculate our standard deviation estimate turns out to be too small. So what we do to compensate for the smaller sum is, instead of dividing by n, divide by n minus 1, which it turns out is the degrees of freedom. We use this simply because it gives us a better estimate of the population standard deviation, which is why when we do not know the mean of the population, we use S equals the square root of the sum of the variances divided by n minus 1, which is also why, if you recall back when we came up with statistics for quantitative variables, that is the difference in what your calculator reports for standard deviation between Sx, our sample, and sigma x, which is our population standard deviation. Final words of caution, and then calculator practice. Don't confuse proportions and means. I've already seen it in some of your guys' work you submitted. I know we have a lot of practice with hypothesis testing about proportions, but proportions and means are different because categorical and quantitative variables are different. Examine the normal condition closely. If we ain't normal, we are done. So beware of multimodal distributions. The nearly normal condition clearly fails if a histogram of the sample has 2 or more modes. Doesn't work. Beware of skewed data. If the data are very skewed, we can try re-expressing the variable. We've practiced that before. If you have outliers, what we need to do is run tests both with and without the outliers, and we report the results for both. We've seen each one of these techniques. These are just good practices when your data is not normal. So let's jump into this calculator practice. Let's say that in previous years, the average temperature for this time of year is 67 degrees Fahrenheit. Students are complaining that this year it's much warmer. To find out, the students record the temps at noon for a random 2-week period. For this example, we're going to assume that this population standard deviation is 5. So given these temperatures, test the student's conjecture at a significance level of 0.05. That's our alpha. This is the purpose of becoming familiar with the calculator. The data is most appropriate for a t-test, but we will be running both a z and a t-test. We know the population mean, but we do not know the population standard deviation. So we should be using a t-test. Remember the notes from before. If you don't know the population's standard deviation, that's your hint to use a t-test over a z-test. But for educational purposes, I'm going to show you how to do both. So we are measuring the mean temperature of this time of year, with our hypothesis being that it's either our mean temperature is equal to 67 degrees or it's going to be less than or equal to. And our alternate hypothesis is that our mean is higher than 67 degrees. So let's run through our assumptions and conditions. Our independent assumption, and we can see that our temperature measurements are independent. Our randomness condition, the days were chosen at random. And then our 10% condition. 14 days is certainly not more than 10% of the days we could measure. Next, we're going to check the normal population assumption and see if we are nearly normal. 14 days is a small sample, but temperatures for this time of year are distributed normally enough around the mean temperature. We can check using a histogram or a normal probability plot, shown here. Since this is learning the calculator, we're going to be finding both Z and T. So we have our list. We're going to enter it on the TI Nspire. I'm going to name it temp. If we wish to find a critical value, we can always do inverse normal, 0.975, because our significance level is 0.05. We hit enter and we get 1.96, which is what we expect. So to find our Z test, we're going to hit menu, statistics, tests, Z test, and we're going to select data. Our mean hypothesized is 67. Our population standard deviation is 5. We're going to use the temp list with frequency of 1. Our alternate hypothesis we're testing is that it's greater than our 67 average. So when we see our results for our t-test, we get a p-value of 0.0162, which means we should reject our null. And you also see that we have a z-score of 2.138. If we wish to find the critical value for the t-value, so the critical t-value, we're going to hit menu, stats, distribution, inverse t, and then we're going to type in 0.975 with a degree of freedom of 13. And you should get a critical value of 2.1604. To find and run a t-test, we're going to hit menu, stats, tests, t-test, and we're going to select the data option. With our mean of 67, we're going to use our list for temperature. And again, we're testing our alternate hypothesis that it's greater than mu. And if we get our result, we'll see a t-value of 2.28. And we're comparing that against our critical value of 2.1604, which obviously it's larger. If we look at our p-value, we get a p-value of 0.0197, which means that it's less than our significance level of 0.05, and we're going to reject the null. If we know the sample statistics, we can test the hypotheses using the sample mean and standard deviation. We will compare a sample mean to a known population mean using the hypothesis 135, and our alternate hypothesis, it's not equal to 135. So suppose the population has a standard deviation of 32 pounds, and our sample had a standard deviation of 31.5 pounds. Would a sample of 38 items weighing in at 138 pounds be enough to reject the null hypothesis? So we don't have any data to enter in this case. Instead, we have statistics. So if we are going to run a z-test, because we know the mean and standard deviation of the population, we're going to hit menu, we're going to go down to statistics, tests, and z-test. Instead of data like the last time, we're going to use stats with our mean of 135, our population standard deviation of 32, our x-bar, our average of our sample is 138, our sample size is 38. We are going to say that they're not equal, so that's our two-tailed alternate hypothesis, and then we hit enter. And we get a z-value of 0.577, which means the p-value for this test would be 0.5633, which is clearly above our significance level of 0.05, which would lead us to fail to reject the null hypothesis. If we use the same data to conduct a t-test, If we want to find the critical value before, we would use inverse t of 0.975 with degrees of freedom of 37 because our sample size is 38. And the critical value that we're comparing against is equal to 2.026. So if we go to our t-test, we're going to hit Menu, Stats, Tests, t-test. This time we're going to select Stats with our mean, again, of 135, our sample average of 138, our standard deviation for our sample is 31.5, and our sample size is 38. Our alternate hypothesis is we're testing if they're not equal to each other. And then when we hit enter, we see a t-value as opposed to a t-score instead of a z-score of 0.587. And a p-value, the probability we get this, is 0.5607. Very similar to the z-test. Again, because this is above our threshold, our significance level of 0.05, we fail to reject the null hypothesis in this case. So I hope that this was informative. Hopefully you learned something about using your calculator and putting these in context. I look forward to reading your responses as we move on to chapter 24.